I just don't have the time to show the proof to you. If you're curious about the proof, I can point you to a very good textbook that does a really cool, elegant proof of it. But I'm just sort of standing on the shoulder of the giant again and showing you that. To set up Green's theorem, you need to make sure you have a closed path, and this is what the double integral calculation turns your dx dy type of line integral into, a double integral calculation. So you're actually, instead of integrating along each of the paths themselves, you turn it into a double integral over the interior region of the path. And then it turns into like a test 3 problem, a double integral problem. So, old things about double integrals, don't forget them. You know, if you're integrating over rectangular regions, then it's going to probably be good to leave it in x, y coordinates. But if you have any kind of circular or maybe semicircular regions that your loop makes, you may want to consider using a double integral in polar coordinates, okay? And also, look for things like x squared plus y squared popping up as you construct your Green's theorem integrand, okay? So, if I want to calculate this line integral here, instead of going, you know, one curve at a time and evaluating 4 separate line integrals for 4 separate parameterizations, what we can do is this. Turn this into the double integral over the interior region D of this. Oh, huge point that I really need to outline here in red. I mean, we're still setting it up right, but this line here underneath the statement of Green's theorem is very, very, very important. Because whenever you're dealing with this version of a line integral and you plug in the parametric path, you plug in the x equations and the y equations and the x derivative and the y derivative and so forth, turning it into a t integral, the orientation of the path plays a big role in terms of the direction of the valuation of the integral. So whenever you turn this into this with Green's theorem on a closed loop curve, the understood orientation for the curve is always going to be counterclockwise. So the only time this can become this is if you have counterclockwise orientation on your loop. The only difference is, if you happen to notice, and you kind of have to have an eye for it, or maybe a little hint, watch out, it's clockwise here. If it goes to clockwise orientation, the only thing you do is either do this and take the opposite of your answer, because that's the only thing it would do is cause a sign change. Or you could turn this into p partial y minus q partial x instead. Okay? I usually just evaluate this and just take a negative in the front if the orientation is clockwise instead. So I need to outline that in red. I mean, I've already got it written here in bold, but huge big asterisk on both sides of the statement in red. Green's theorem assumes that the curve's orientation is always going to be counterclockwise. So again, when you set this Green's theorem up, double check the orientation to make sure you have that counterclockwise, setup. Then you can turn this into this legally and go ahead and evaluate it using Green's theorem. Okay. So this is counterclockwise. Green's theorem checks out. I don't need to put a minus sign in front of my double integral, so we can sound it forth. All right. So let's do the integrand first. The integrand is q's partial with respect to x, which xy is my q, so that's going to be y, minus p's partial with respect to y. P depends on y only, so 2 minus y squared would become negative 2y. So watch out for the minus minus. There's a minus inherent to the Green's theorem, but then your partial of p with y is also minus 2, so that should become 3y before you integrate it. Then, before I write d anything else, let's commit to what order you want to integrate in. This is the region that we're integrating over, this square that has 1 by 1 dimensions in the first quadrant. Is there any one particular order that's easier than the other? Yeah. Constant limits, so we can just as well do dx dy or dy dx. So I'll just choose alphabetical order. And since it is a square, your x limits, x goes from 0 to 1 no matter which way you enter and exit. Y, then you flatten to the y-axis, y goes from 0 to 1 also. And so that's what Green's theorem transforms this potentially tedious line integral into, in terms of evaluating along all 4 of those paths. Oh, let me finish. Sorry. 0 to 1, 0 to 1. I'm integrating 3y, I believe. So if I integrate with respect to x first, that gives me 3xy. And so that equals 3y minus 0. And then I integrate that with respect to y last, and that should become 3/2 y squared you plug in those limits, you get 3/2 as your final value. I know I'm asking you to take a big leap of faith. I mean, it would take us parameterizing each one of these paths. Like this one, you'd have to parameterize as you're starting at the point 0, 0. Your direction vector would be 1i. So there's the parametric equations for that particular part of the curve, and we'd have to call that C1. And t would have to go from 0 to 1 there. Then to go along this part of the curve, C2, you're starting at the point 1, 0, so 1 for x and 0 for y. Do y'all see where I'm getting these parametric equations from? Remember, the two things you need to get a parametric line segment is the beginning point. The point that it begins with is your constant terms in each equation. The direction vector are the t coefficients in each equation. So I began at the point 0, 0 here, and the direction vector is just going to be 1i to go one click to the right. So I need a 1 for the t coefficient on x, but I have no t coefficient on y. And that should make sense. If you're on a horizontal line segment, your y value should stay constant for the direction of that line. Same thing here. Who's going to be constant on this one?
Y.
X, because you're on a vertical line. So x will always be 1, okay? Well, you start at the point 1, 0, so you pair 1 with x and 0 for y for the constant terms. What's the direction vector that would take you one click north? 1j. So that means you have a 0 t coefficient with 1, and you have a 1 with the x, and then you have a 1 t coefficient with y. You see? So you all... Oh, and then what t restrictions would that require? 0 to 1. If you always use the direction vector as the actual vector connecting your 2 points, see, to go from here to here, the vector that connects 1, 0 to 1, 1 is 1j. If you use the actual vector that makes that line segment, then you always will have 0 to 1 as your t components. Every single time. So what about parameterizing this one? What would your constant terms be? 1 and 1. Oh. And then what would your, who would actually have a t component, or a t? The x. Because your direction vector is actually going left is minus 1i. So you have a minus 1t and then no t with the y because you're staying horizontal. And still, since negative 1i is the only vector that takes me from here to here, I'm still getting away with 0 to 1 for my t limits. And then to go from here,
x is 0, y is 1 minus t.
X equals 0 and y equals 1 minus t, 0 to 1. So parameterizing line segments isn't too bad as long as you get the idea down pat. The point you start with is your constant term, and then the full direction vector that goes from beginning point to end point, if you use that, you can always use 0 to 1 for t. So this direction vector is negative 1j. So you put a minus 1t with your y, and every single one of these segments use 0 to 1 for your t limits. Now here's the thing. You'd have to actually calculate 4 different line integrals. So to calculate the first contribution, you'd plug into this. You plug in 2 minus y squared. So in this case, on C1, that would be 0, because you're replacing y and x with their parametric equations for that particular curve. So this would be 2 minus 0. dx would be the derivative of x, which is 1t, or no, lie, 1 dt. And then plus x times y, that goes away. So therefore, so does the dy that goes with it, because your y equals 0. So really, you're just integrating 2 dt from 0 to 1. So if I integrate 2 from 0 to 1, that should give me 2, right? Someone jot that down, 2. Okay? Now for this one, for curve number 2, going from that bottom point of the square to the top point of the square, starting from scratch, this would actually be 2 minus t squared, so I may need to start writing this one down. The first one we could get away with. So the line integral for C2, 0 to 1 is going to be my limits. 2 minus y squared is going to be 2 minus t squared, because y equals t on that curve. dx, well actually, what's dx there? dx is the derivative of my x equation. 0. So, start over. That's all going to go away since dx wipes everything out. And then x times y is going to be 1 times t times dy, which doesn't go to 0. So dy would be 1 dt. So along curve number 2, we're integrating t from 0 to 1, which is half t squared, 1/2. So far we got 2 plus 1/2. Starting kind of shallow. Oh, well, technically we're already more than we have. You know, we already have more than what we need with the value of the final answer we got from Green's theorem.
Oh, you subtract 2?
Well, we may have some negative line integrals in there too that we'll subtract out. So hopefully that's obviously what's going to have to happen, because now we're on C3. So if I integrate along C3, and I always want to complete that with PO. But anyway, if I integrate along this curve here, starting with another copy of your integrand, 2 minus y squared is going to be 2 minus 1 along C3. So that's 1. dx is negative 1. So 1 times negative 1. And then plus x times y. X times y is 1 minus t times 1. And then dy, 0, because y is a constant, so you can erase all that. So you're really just integrating negative 1 from 0 to 1 here. So now we're back, we subtracted 1. And that's technically our integral's value. So what should the integral for C4 have to be?
0.
Should be 0. So C4, x is 0, y is 1 minus t. So 2 minus y squared, no matter what that is, dx is going to be 0. So that wipes that whole part of the integrand out. Also,
0
x times y is 0 times, going to wipe everything out there. So you're really integrating 0. You ever thought about integrating 0 before? No, not so much. I mean, it technically gives you a constant, I guess, but then when you plug these limits in, it's constant minus constant, so it's just going to go away. So, you know, if you integrate 0, you're going to get 0. So along these 4 curves, our line integral individual values were 2, 1/2, negative 1, and 0. So if you add all those up, 1.5. So Green's theorem trumps that, in my opinion. If you've got a loop curve, think Green's theorem. Think, you know, q partial x minus p partial y, double check your counterclockwise orientation, and then evaluate as a double integral, a lot easier. Yeah. I just wanted to make sure, I mean, that's by no means a sufficient proof of Green's theorem, but I just wanted to let you know, at least seeing the consistency, it's a little more believable now. Right? And plus it is, you know, up here in print, so that gives it a little more, you know, officiality. Okay, so Green's theorem applies here, yes, no, maybe?
Well, since it's
Should.
on paper,
It's at least on the same piece of paper as the introduction to Green's
Not going
theorem.
the same direction.
But good eye. Yeah, your orientation here is actually clockwise. So watch out, beware. So what that means is, since you have clockwise orientation with a big red box around it, that means the double integral here is going to actually be the opposite of, and you can still use it as, you know, q partial x minus p partial y. Just give me some indication that you're going to take the opposite sign, because the orientation is not counterclockwise. So, and usually that's what I do, is I put a big minus in the front because of that clockwise orientation versus counterclockwise.
Oh, you said we can just do py minus px.
Or you could, if you distribute the negative inside here, that does reverse the order of subtraction to p partial y minus q partial x. However, don't do both. Put a minus in the front and you reverse that order, you're evaluating the regular Green's theorem, because you really just multiplied by 1. So yeah, just one or the other, just not, you know, not simultaneously. So negative in front, q partial x. So again, alphabetical order. P is always paired with dx, q is paired with dy. Q's partial with x here is 8xy minus p's partial with y, which is 12xy, and I'm holding off on my d just yet. Well, I guess I could just say dA. So technically we're integrating negative 4xy. So now, if you want to, the negative from the clockwise orientation can hit the negative inside from doing the Green's theorem, and you can make that positive because that's just negative times negative. So I think I will do that. So now setting up our limits.
Should we switch to polar?
I think we should switch to polar because your region D here, the interior here is, it looks like a quarter annular region between a radius of 2 and a radius of 4. So, and ideally the wording of the problem would kind of build your confidence to let you know. It would say that, you know, the curve shown at the right is, you know, consists of 2 quarter circle arcs, one of radius 4, one of radius 2. So that way you could readily take advantage of the fact that, okay, those aren't parabolas, those are circles, I can use polar. Okay. So if we do polar, and that was grammatically correct, R goes from
2 to 4.
2 to 4, oh, 2 to 4, and then theta,
0 to 5.
0 to pi 2, yeah.
Just like
That's okay. No, it's not, but you know, just you fixed it, right? So my polar limits.
Now we do the R.
Yes,
the RD
because I'm going to put my polar limits on the outside, but we also need to convert our integrand. Yes, the integrand is 4xy. So unfortunately, you don't get the x squared plus y squared love here. You got to go back to the other conversions.
Be 4 cosine theta.
Yeah.
4 sine theta.
Yeah, with r cubed. Yeah, because x gets replaced with r cosine theta.
Yep.
Y gets replaced with r sine theta. There's the Jacobian r. We're committing to dr d theta order. So again, sorry, I've shrunk my handwriting for some unknown reason. So that should be what 4xy converts to when you convert it to polar. I'm going to take advantage of the constant limits and do this. Integrate 4r to the third with respect to r.
You guys zoom out.
Oh, sorry. Integrate 4r to the third with respect to r, and then integrate sine theta cosine theta with respect to theta. So you see what I did there? Anytime you have constant limits and you can factor the integrand, that's always good to do when you can do it. That one's going to be straightforward powerful. R to the fourth. So that'll give me a 16 minus, no it won't. 4 to the fourth is 256, yeah. It's 2 to the fourth is what I was mistakenly doing first. So the R integral gives you a value of 240 times whatever this theta value is going to turn into. Being a math teacher, when I see sine times cosine, this is what I always see. Sine theta, cosine theta. If you had a 2 in the front, it's the same thing as sine 2 theta. You know, one of those little kind of kick to the under the bus formulas from trigonometry, the double equal. And if you don't have the 2 there, you can just cut this in half. So would y'all mind? I mean, you could do it. You could do it u sub easily. I mean, just let u equal sine theta, du is cosine theta d theta. You get 1/2 sine squared. You can integrate it in terms of u. But I just kind of like this. It's not a u sub. It's just a trigonometric replacement. And it's something I've always kind of just picked up on. Anytime you see sine times cosine, that little double angle identity tells me I can replace sine times cosine with 1/2 sine 2 theta. And then when I integrate this, it becomes negative. The trig function becomes cosine 2 theta with the negative. But what is your coefficient with that? 1/4. Because yeah, you got to divide by that extra half. And again, the answer to this gets multiplied by 240 over there on the left because we did the whole factoring thing. Pi over 2 plugs in, so I'm taking the cosine of pi. And that's -1 times -1/4, so it should give me a positive 1/4. So I better start writing this down because I'm about to make a mistake. 1/4 minus, when I plug in 0, the cosine of 0 is 1. So you keep the negative on the quarter. So watch out. It's tempting to make a mistake and say that that goes to 0. Actually goes to 1/2. So since I need to multiply these two results together, 240 times 1/2 takes me to 120. should be the value of that line interval. Okay. Any questions so far? Well, too soon to tell. It's very premature.
And that's just measuring the length of the line?
Well, see, this is one of the more abstract line intervals. The dx dy type is kind of like, if you look back at the f dot dr, well, my purple's giving up on me. Where you have p and q as the components of a vector field, and dr is like r prime. So if you think of that as derivative of x and derivative of y from r prime, if you do the dot product of f dot dr, it produces the product of the I components plus the product of the j components. So anytime you see one of these line integrals that has the dx and dy separated, it's like some third party has come on and said, well, p and q are the vector field components, dx and dy are generic representations of x prime and y prime, so this is what the dot product looks like. It's like they've done the dot product already. So if you decipher this as a vector field problem, the components of the vector field will be 6xy squared and for I component and 4x squared y for the j component. And then the dx and dy is left generic because you've got more than one curve defining the line integral here. Because if you go back to doing it the old way, you'd have to do it like we did the square up there at the top. You'd have to do wrong way, C1, C2, C3, C4. And then turn it into 4 separate line integrals. So it's kind of like the dot product's done. That's what the form of f dot dr would look like for some vector field. Now that you've got it in that format, Green's theorem makes it an easier calculation. But keep in mind the Green's theorem only works when you have a loop curve. I probably didn't make too big a point of that, but that's the only legal time you can do Green's theorem is when you can turn it into a double integral over a two-dimensional closed-off space like that. Okay. There is a three-dimensional version of Green's theorem. It's unfortunately one of the topics that we kind of had to kick out. It's called the Divergence Theorem. See, this is sort of calculating line integrals in 2 dimensions on a closed curve. The analog is calculating, well, line integrals through space, but really they're surface integrals through space over a closed surface, where you have a distinct interior and a distinct exterior. And it turns into a triple integral over the 3D region that you're integrating over. So maybe it's like a sphere. So you do a triple integral after doing the divergence theorem, and maybe use spherical coordinates if you're integrating over a sphere or something like that. So I don't think you're going to be any worse for the wear, though. Okay. Any questions or what ifs or pensive moments? Yes, sir.
What is this giving us?
What is this giving us?
Works.
If you think of it as work, if you think of this as the dot product that's already been done, then the p and the q here are like the components of a vector field. And you're calculating the total work done by vectors in this field that would have those as its components in moving a particle along that quarter annular curve. So it's still calculating work if you want to think of that. But it's like someone's already done the dot product of f dot dr. You don't have to actually do the dot product yourself. And the reason that is because you've got more than one curve made up here. So that's why the dx and dy are kept generic as opposed to, well, plug in 2t squared for the dx and 3t for the dy and make the substitutions like we did earlier. Okay. Yes, sir.
So to put this in physical terms, would this be like how you would determine the sorts of vectors that would be acting on, say, like a buoy or a balloon for it to move in a specific pattern, like that one, say, right there?
Oh, like if you had if the vector field represented, say, wind current, and the work done in moving
or water
it.
current, or just whatever.
Yeah, work done in moving it in that particular path.
That,
Yeah,
so okay.
yeah. That's not a bad analogy. Yeah. It'd be kind of funny to see that, though. Balloons making very curvy and hard right turns, just at random. Okay. I'm debating. I've decided not to start parametric surfaces. I was going to start parametric surfaces tonight, but parametric surfaces get me really excited. And so I'm going to have to I want to just start off class on Tuesday with parametric surfaces because it's really, really cool. The only parameterizing you've done this semester is with lines. you know, going from a point in 2D to 2D or 3D to 3D. You know, you need 2 points, a direction vector, and things like that. But if you parameterize a surface, how many parameters do you think you're going to need?
All of them.
Okay, well think about go one dimension less. To parameterize a line segment or a helix in space, how many parameters did you need?
2.
Well, you need 3 equations, but how many variables were used in the parametric equations of a line? 1. Because for a line segment or even a curve in space, your parameter is just essentially one-dimensional, and you're taking it and mapping it to a line in space like that. But if you want a surface in 3 space, you've got to have a 2-dimensional domain that your parameters come from to kind of wrap them, kind of like a skin that you apply to a character on a you know, RPG, sort of wrap the surface around the shape itself and kind of, you know, map it there. So that's what, I get really excited with this. We'll start that on Tuesday. And it is the next section in the notes if you kept everything in order, all right? So y'all email in if you have any questions. The test keys for 1, 2, and 3 are posted on our D2L page. Practice like crazy. The tests are manageable. Okay, you should be able to do them, no problem. Just go do a dress rehearsal with the old copy. Crack at the new one.
Same thing with different numbers?
Pardon? Just change the numbers. Yeah.
So we go through the test again and just change the numbers around, basically doing the same thing?
Yeah, you could probably make out your own version of the retest. And you might get lucky and come up with the same problems I came up with.